All right, so I'll answer that question in a moment. So at the server end, so whatever it is actually happening is the decryption is happening first and then the verification is happening, right? So whatever the content that the server got from the client is actually, the server is actually blindly using the key to decrypt the content, to compute the MAC, and then to compare the MAC to what it was sent. All right, so what would go wrong here? The receiving party decrypts the data using the session key and verifies its authenticity. All right. Just to answer your question, the receiving endpoint decrypts the data by using the session key and then verifies authenticity. So what's actually happening is, unfortunately, this means that unauthenticated attacker can send arbitrary messages, all right, though the attacker can actually modify some content in the middle or some junk packets bombarded at the server and making them to, making the server to decrypt every, junk packet that the server actually received, all right. The receiving endpoint must decrypt them first in order to verify the MAC. That was as per the design. If you see this, it is computing the MAC first and then encryption later, okay. At the decryption point, you have to decrypt the ciphertext to get the plaintext and compute the MAC, all right. That's what's happening. The receiving endpoint must decrypt them in order to verify the MAC. What could go wrong? The attacker actually can flood the server with all of the junk packets, some arbitrary encrypted, we don't know with what key it was encrypting. But the decryption still happens, right? And making the server to decrypt, resulting in denial of service attack. Let's say you're bombarding the server with a lot of junk packets. You have a botnets all over the world. You can actually initiate an attack with the botnets targeting the server, all right? So the botnets can actually send some junked ciphertext information targeting the server, and the server would actually end up in decrypting that. And after the decryption has been done, the server actually verifies the MAC, and the MAC would actually fail, and server will discard the message. So what is the intention of the attacker here? The attacker is basically trying to perform a denial of service attack. The attack is on the availability of the service, right? Not on the confidentiality, not on the integrity. Okay, this is a very clever attack. Okay, so if you see the decryption time for the packets, for 1,000, these are just approximate value. For 1,000 packets, it's using this milliseconds approximately. Now you might ask the question, if the attacker is actually appending a ciphertext, right? Now he can actually recompute the MAC, append the new ciphertext, and send it to the server. All right? The attacker can still do that. But is it possible? Attacker cannot force the MAC without knowing the session key, right? So what is computed on the plaintext is a session key. The MAC using the session key. So the attacker should know the session key to recompute the MAC and to attach to the modified packet so that he'll actually make the server to accept it. But the attacker cannot touch it. Why? Because he should know the MAC by using the session key. But the session key is private to only client and server. All right. So, yep, the same thing. This is the message authentication code. You're using the secret key to compute the MAC for the message. So pass through a MAC function along with the secret key to get the MAC. All right? Only the secret key is known to client and the server. So this is a problem, right? So what can we do now? You can actually send multiple